In the last video, we saw how to do Lewis structures for atoms and simple ions. In this video, we're going to see how you can put together atoms and have them share electrons to satisfy their octets. Let's start with the simplest molecule that there is, H2. Now, if I draw the Lewis structures for the atoms that are inside there, there's one electron in the valence shell for hydrogen. So there'll be one dot there. And here's the other one. All right. Now, what can they do to get an octet? How can they come together to make an octet? Well, they can't. They don't really want an octet. They want to be like the nearest noble gas, which is helium. Helium's got 2. So if these hydrogens could get 2 electrons, then they'd be satisfied. Now, we could have this one grab the electron from the other one, but then the other one's not going to be happy. And why should they do that anyway? They're both identical. And what they will actually do when they come together to get 2 electrons is share the electrons. They'll say, both of these belong to both of us. And now they both think that they've got 2 electrons like the helium. I could write the Lewis structure like this. There's an electron pair between the 2 hydrogens. Now this is going to hold the the molecule together. Here's one of the hydrogen nuclei, and here's the other hydrogen nuclei. And here are those 2 electrons wedged between them. Now if you get this cloud of negatively charged electrons wedged between 2 positively charged nuclei, they are going to be attracted to that cloud. And then it's going to bond them together. So when you put 2 electrons between 2 nuclei like that, you're sticking the molecule together. You're making a chemical bond. And in fact, we usually don't write shared electrons like separate dots. We write them like a bond, like a stick. This stick means 2 shared electrons. You can call that a bonding pair, or you can just call that a covalent bond. That's how we represent covalent bonds in Lewis structures. You could call that stick either of these, but there are 2 electrons inside there. We draw it as a stick. Let's do a molecule that's a little bit more complicated. How about a water molecule? That's H2O. Now let's write down the Lewis structures for all of the atoms that are in there. There are 2 hydrogens and each one has 1 valence electron. There is an oxygen which has 6 valence electrons. And I can share electrons until they're all satisfied. How many does the hydrogen want? It wants 2. So it will like to share an electron with a neighbor. Now, the oxygen is still not satisfied by that action. The hydrogen is happy, but this oxygen still isn't. It thinks it has 1, 2, 3, 4, 5, 6, 7 electrons. How many does it want? According to the octet rule, it wants to be like the nearest noble gas, which has 8 in its outer shell. So it wants to get another electron. Now, if this hydrogen shares that electron like that, now the hydrogen thinks it has 2, so it's happy according to the octet rule, and the oxygen thinks it has 1, 2, 3, 4, 5, 6, 7, 8. So it's happy too. It's satisfied the octet rule. We say it has a complete octet, that oxygen, because it has a set of 8 electrons around it, and that includes all the shared electrons with its neighbors. So we could write this formula down like this. But usually when you have shared electrons, people will write it down instead like this. So we have 2 shared pairs, 2 bonding pairs, and 2 unshared pairs. So this is something new. We have 2 unshared pairs. You call an unshared pair lone pairs. So you can see in the homework when they ask you about a Lewis structure to count how many bonds do you have and how many lone pairs do you have. You'd say in this molecule you have 2 bonds and you have 2 lone pairs. Now we could keep going like that and build more and more complicated molecules by puzzle piecing them together like this. But this gets a little bit tricky when you have more and more atoms. It becomes a little bit more difficult to bookkeep the electrons because you can't write down extra electrons to satisfy things or take electrons away. You are stuck with the total number of valence electrons that you've got in the molecule. And what you're basically doing when you're doing these structures is taking the total number of valence electrons and dealing them out across the structure. So look on your modules page. You'll see an item called How to Draw a Simple Lewis Structure. And this is a step-by-step guide for putting together Lewis structures by dealing out the total number of valence electrons that you've got. Let's try that step-by-step procedure and build the water molecule again using that. The first step in the recipe for drawing Lewis structures is write a skeleton structure. A skeleton structure is kind of a roadmap. It shows you how the atoms are hooked together. And it doesn't show you in an exact way. It shows you one of the atoms will be in the center, and usually the other atoms are around the outside in a simple molecule. Now, I've got H2O here. How do I do a skeleton structure for it? Well, I have to decide which atom I want to put in the center, and then which ones are going to go on the outside. Here is a simple rule of thumb that works most of the time. The closer an element is to the center of the periodic table, the closer it should be to the center of your structure. So if I look at hydrogen, it's on the edge of the periodic table, and if I look at oxygen, it's 2 columns in. So the oxygen should go into the center of the structure. See, in my structure here, the oxygen is in the middle, and the hydrogens are on the outside. Now, it doesn't matter where I put the hydrogens. If you would have done this as a skeleton structure, that'd be fine. It's not really showing you the 3-dimensional arrangement of atoms in the molecule. It's showing you more how they're hooked together. So let's take that as our skeleton structure. The second step is to count all the valence electrons and throw them in a pile. Now, how many valence electrons have I got? Well, let me see. I've got a hydrogen, another hydrogen, and an oxygen. The hydrogen, if I look at my periodic table, has 1 valence electron. So does this one. And the oxygen has got 6 valence electrons. So the total number of valence electrons is 1 plus 1 plus 6 is 8. I've got 8 valence electrons to deal out. All right. The next thing that I do is connect my structure. And I do this by drawing a stick between the central atom and each of the outside atoms. So here's my skeleton structure. I'm going to draw a stick between the central atom and each of the outside atoms. So I drew 2 sticks. Now what does that cost me? I had 8 valence electrons to start with, and each stick costs me 2 electrons. I drew 2 sticks, so that's 2 4 electrons that I took away, and now I have 4 left. Now as I do this recipe, I have to bookkeep the electrons. So you start off with your initial count. Every stick you draw to connect the structure is going to take away a pair. So I took away 2 pair of 4, and now I've got 4 left. The next thing I'm going to do is satisfy the outside atoms by dumping valence electrons on them if they want any more. Now, if I look at this one, are those outside atoms satisfied? Well, yes, they are. Hydrogen only wants 2. So it's got 2. That stick stands for 2, so it's got what it wants. What about this hydrogen? Is it satisfied? No. Or yes, it is, because it's got 2 electrons in the bond. So all hydrogen ever wants is 2. So hydrogen is just fine that way, so there's really nothing I have to do to satisfy the outside atoms with this particular simple molecule. We'll do another one later where we do have to satisfy the outside atoms. The next thing I want to do is dump all the remaining electrons after the outside ones are satisfied on the central atom. Okay, so I have 4 remaining electrons. I want to dump them all on the oxygen. And remember that thing about I'm going to dump them so that I have north, south, east, and west positions kind of filled up. So there'll be a pair up there and a pair there. And now I'm going to ask, is the central atom satisfied? If yes, then you're done. That's all you have to do, and that's the Lewis structure for the water molecule. Alright, in the next video we'll do one that is a little bit more complicated than this.